So 20-1 was the first section that we covered, but that was a while ago, right? What was 20-1 about? Good. Electric fields. Electric fields. Now, again, as always, we can do questions on the problem set that you guys have, but I want to just give a quick blurb about the test so you have an idea first. So electric fields. Electric fields are caused by source charges. So something that has an abundance of charge generates a field around it, just like something with mass generates a gravitational field around it in the same way. Now, the formula from section 20-1 for electric field was this. It was Coulomb's constant.
Q2.
That's for Fe, yeah. So this one is just KQ over R squared. The other one was KQ1, Q2 over R squared. So remember, this is the electric field, not the electric force in this example here, or in this formula. Now we can figure out the electric force on some other charge by taking the electric field that we calculate and multiplying it by that other charge. So this was something we wrote as a second way of looking at the formula, where we said, hey, this is how you calculate electric field from the source, but what if I suddenly bring another charge near the source? Once you calculate the electric field from the source, you can take that electric field times the charge of the other charge and get the force between them. So this avoided using KQ1, Q2 over R squared.
So just to reiterate, the top equation has to do with distance, whereas of the electric field, the radius, whereas the bottom has to do with like the force of it.
About it, Nick? Yeah. So this is the electric field, but this is involved with a source that's emitting an electric field. Whereas this is the force between the source and Q0. So if I have, let's say here, I'll give you an example, okay? The eraser has a lot of electric charge. It's sitting still, it generates an electric field around it. Now, I can calculate the strength of that electric field from the first formula. If I know the Q value, which I would know, the amount of charge, and if I know how far away I am. So let's say I'm standing where I am now. Let's say this is about a half a meter. So R would be a half a meter, Q would be the charge on this object, and K is a constant. But now in the second formula, what if suddenly I bring a proton, the marker, a proton, and put it right here? Now, the proton is at the same distance I was, which is a half a meter. So now I've got the charge of a proton, and that's going to go in for Q0 here. And if I want to find the force that this feels attraction or repulsion, either one, between the source and the proton, I can take the electric field I calculated a minute ago from the source and take that electric field and multiply it by the new charge that's been brought near the source. So this is a way to calculate Fe without having to do Kc Q1 Q2 over R squared for two arbitrary objects. So if you find the field around one object first, you could then simply multiply that field, E, by whatever the other object's charge is, and that'll give you the force of repulsion or attraction between these two objects. So in the first scenario there, when you're calculating electric field, there's only one object, and it's the source. So when you're calculating electric field, this is the source, and that's some point in space. Okay, this is some point. So you're calculating the electric field at that empty spot from the source. But in the second scenario, you're now taking a proton and you're putting it right there at the empty spot. And we're calling that proton Q0, whatever the charge is. And a proton charge, you should know. The proton is this fundamental charge, and it's on your formula sheet. What's the proton charge at the bottom of your formula sheet? It's E. Very good. What is that number? That's Kc. 1.6 times 10 to the negative 19. That's the charge on a proton. So the minute I bring a proton to this empty spot, now there's going to be an attraction or repulsion between these two, and I can calculate it by using the same answer I got in the first part and just multiplying by the charge of a proton or an electron. Okay, remember, for most of these problems, we're really calculating the magnitude. And then we know whether it's attractive or repulsive based on the charge. So let's say the source was positive and then you bring a proton. That's going to be repulsive. So you're going to calculate it and then write the word repulsive.
Wait.
Or if it's attractive, you would write the word attractive. Hold on. Helen?
You always assume that the source in electric field is positive, right? So like the E, whatever, if your E is positive, then the lines in the diagram are going to be moving away because you're assuming that it's...
If the source is positive, you draw the lines away. If the source is negative, you draw the lines towards.
Oh, I was doing a problem set, it's definitely you should like assume that like it's usually a positive source.
Not source, you're confusing the word. So
Usually a positive
Put a charge in.
charge,
It's
yeah.
usually assumed as
that's being affected by the source.
Yeah.
So the source is whatever it wants to be. But if the source is positive and we assume this is positive, which way is this going to move? Away.
Yeah.
But if the source is negative, which it can be, and this is positive, it's going to move toward. That's how you draw your field lines. So your field lines for a negative source are drawn toward.
Yeah.
The field lines for a positive source are drawn away. For that reason. Okay, for that reason.
Yeah, so an example problem, isn't that the ones where we had like 3 charges in a linear function?
That was from last chapter, where there was 3-point charges, and you have to find the overall force acting on one of them.
Is that 20-1 or is that something else?
No, that was 19.2 and 19.3. That's
Oh,
what that was
yeah.
for.
That's 21.1 was the circuits.
21.1 was the beginning of circuits.
Yeah.
Beginning of
So it
circuits.
would just be like a written problem.
Yeah, this is going to be a problem very much like what you're seeing on the board here, where I have you calculate the electric field, and then tell you, okay, now there's an object that's charged, brought in range of the electric field, find the force. So you take the answer from part A you got for the electric field and multiply by that new charge, and you get the force felt. So there's no need for the older formula from 19.2 and 3. Helen, you were going to ask something. You said, hold on, and then I went to Helen.
Okay, so basically, if you want to find the electric field, it's use that, and then if it's like a part 2,
Mm-hmm.
and you have to find the force, you use what you find for E for there.
And then whatever the new charge is that I introduce.
But will you will give us?
Of course, I'll say it's a proton or electron, and then you know the
That's
charge, 1.6.
1.6. For proton and electron, it's 1.6.
It's the same, yep.
Okay.
Now, if I say it's 2 protons, what are you going to do to that charge? Exactly. Precisely, yep. Very good. And if I tell you that the original source was positive, and I bring a proton near it, that's going to be repulsive. If the original source is negative, it is attractive. Okay? It's really the only way I can vary these types of problems up when it comes to the test for 20-1. Okay, for electric fields. Now, there was a lot about electric fields. You got to know your general field diagrams. Your general field diagram. What I mean by that is know what the positive and negative source look like. That's a good way of thinking here. If I have a positive source like that, my field lines are drawn away. If I have a negative source, my field lines are drawn toward. Okay? Now, if I have a positive and a negative source near each other, what we notice is that the field lines continue kind of overlapping from one into the other like that. We showed that last time. We had a couple of those diagrams. I'm not saying you have to have the diagram memorized, but you should be familiar with these diagrams. Familiar. So that you have an idea on the test, whether it's multiple choice or a quick short answer, how to give a general shape of the field based on knowing the source charge. What if I doubled the source? If I doubled the source, what happens to my field lines?
They increase.
Yeah, the amount of them increases. So if I have double the positive charge on that source, suddenly that's what my field's going to look like. Okay? And I know that you're like, oh, you're just going to draw more lines, it means more, that's not a number. And I know it's not a number, but it's a general schema, right? When you see more field lines coming from a source, it means that that field provided is going to be stronger than the previous one you saw. What else in 20-1? Oh, if there's a point between two fields, we talked about that example also.
The equilibrium.
Yeah, it could be equilibrium or they both. So the equilibrium one, let's start with. Here's the equilibrium example.
2 positives assuming gravity doesn't equal.
Yeah, no gravity assuming, good point. And we've got a proton in between 2 positive sources. Well, both of those sources are going to want to push the proton away, aren't they? So what's going to happen to that proton? If the sources are identical,
It's going to be that equilibrium. Is that
yeah,
what
it's
you're
not
talking
going to move. It's going to be pushed to the right from one source, pushed to the left from the other source. It will not move at this spot or location. And the same is true for two negative sources, even with a proton between them. If that's a proton between two negative sources, the proton's going to want to get pulled to either way, right? I'm the proton. I want to get pulled to one source this way, and I want to get pulled to the other source this way. If I'm being pulled in both directions, I'm not moving, literally. Okay? I'm not moving literally. I would not be physically getting pulled because I'd have two different sources pulling me. Now, if the circumstance presents itself where we have a positive and a negative, again, think about what a proton would do. If I put a proton near the positive source, which way would it move? Toward the right. If I put a proton near the negative source, which way would it still move? To the right. So both of these sources are going to cause a proton to move to the right. You all see that? So if I wanted to figure out the overall field at a location in between or somewhere in general, let's say here, I want to find the field there. Well, you're going to have a field pushing to the right from the negative source, and we're also going to have a field pushing to the right from the positive source. So at this location, the negative source and the positive source are both going to cause a proton to want to move to the right at this spot. So what would I do to these two numbers if I were to calculate them?
You find the
You
distance
add them.
from.
Good, I got this distance.
Yeah.
That'll help me for this one. I get this distance to help me with this strength. But what do I do to those two fields?
You add them.
You add them together, because which way are they both pushing? To the right. To the right. They're both, again, how do I know which way the field is acting? Put a proton here. A proton will get pushed right for both of these cases. That's why I drew an arrow to the right. But in the other circumstance, let's go back up a step now. Let's put the proton here now, in the second circumstance. Now, if I've got a proton there, let me erase the other one if I can, yeah. All right, so here's your proton now here. The proton at this location wants to get pulled to the right from this one. Agreed? Which way does it want to go from this one? To the left. So this proton is getting pulled in both ways. But is it equidistant?
No.
So it's not going to be in a state of. Therefore, if it's closer to this side, which one's going to be a stronger field? The one it's closer to. So what we'd still have to do, though, is this. Take a look at what we'd still have to do the same thing. We'd have to first get the field from the charge on the right, pulling right. Then we'd have to get the field from the source on the left, which is pulling left. And if we're looking for the field from both of these, the one in yellow is absolutely going to be stronger because it's closer to that source. So say I get an answer, and I'm going to pick a random number. 5,000 newtons per coulomb, but 5,000. And this turns out to be 2,000. What's my overall field going to be? 3,000. Which way? To the right. To the right. In this circumstance. So when I look at fields, I have to consider what was called, remember I called the phrase superposition. That was the phrase for this. When you can simply find each field separately and then sum them together. Or subtract them, depending upon the scenario, right? The bottom scenario, we sum together the forces, the fields, because they're both acting to the right. In the middle scenario, we would take the difference between the forces, because one acts to the right and one acts to the left.
What would you give us Q or would you give us R?
I would give you need Q and R for these problems, yeah.
Yeah.
You need both. So this, remember, that this R is whatever the distance is, which is different from this R, right? So the R over here is where this one comes about. The R here is where this comes about. And then you need to know the Q of each of these to figure it out. Absolutely. Yep. Okay, let's keep going. So that's 20-1. It's working here. Whoops, let's go back. So 1 was the beginning of circuits in general. And we started with Ohm's law. This was one of our basic formulas to start with. With Ohm's law, we were able to recognize the inverse relationship that exists between current and resistance. The more resistance we have, the less current. Very good. The less current. Remember, resistance is the opposition to current. That's what it physically is. So when a light bulb slows down the charge carriers to steal and suck away all their energy, they're a resistor. They're slowing down the current to do that. They act as a slowing down mechanism, like a speed trap on a highway, or remember I said a checkpoint, like a police checkpoint on a highway. All the cars have to suddenly slow down. Or a toll booth. A toll booth is a great example, right? A toll booth is pretty much a resistor. It's slowing down the flow of traffic to suck your money from you and then allowing you to go through. It's analogous. A light bulb doing that to an energy, charge carrier with energy. Now, with a circuit in general, we did a lot, right? We talked a lot about circuits. So in general, though, to start, we talked about closed versus open circuits. So to draw a quick schematic, this was our example of a closed circuit right here. How would I open up this circuit? What would I introduce? What thing allows me to open up a circuit?
Circuit breaker that would break the open up on the side.
So either a circuit breaker or a switch. They're the same thing, right? A circuit breaker is a switch that trips on its own. So here's the circuit breaker, and that shows an open circuit now. Now if I press the button, or in the case of this classroom, right? If I press the on switch, I'm closing the circuit there to open the light bulb or to turn it on. But if I want to open the circuit, now I've opened the circuit and there's no electricity. So that's an example of an open circuit shown in that diagram right there.
So is that the way like not a fuse box, but what's the...
Yeah, circuit breaker, fuse box, same thing.
Yeah.
Exact same thing.
When
What happens is this, the circuit breaker senses that there's no element, and suddenly there's going to be a super high current. Because no element involved means no resistance. No resistance means the current's going to spike. When the circuit breaker senses a high current, it trips or opens up a switch, which stops the current from flowing so the wire doesn't overheat and cause an electrical fire.
They can only work on series circuits?
All of the resistors are in series with the energy that they're carrying. But it could be several of them in a row in parallel that are in series individually. So a real circuit breaker would look like this. Here's what a real circuit breaker would look like.
Oh, yes, there's multiple.
So any part of this circuit could suddenly feel a surge of current. So you'll have a circuit breaker in each part. Now, the way I've drawn this is there'd be no electricity at all, right? None, because this is clearly showing no closed circuits. But if I close all of these gaps and literally close the circuit breaker in each of these, then I would have current flowing through each branch. So that's when you go to the panel and you flip that switch over on a circuit breaker physically. What you're doing is physically closing the circuit each time. Okay? But again, if suddenly there was let's say for example, ready? Let's say that this bulb stops. Let's say that this bulb right here stops working, and instead of the bulb operating, the current just flows right through it, and it doesn't get resistance at all, then this would be a really, really high current here suddenly. So this circuit breaker right here would automatically pop open to prevent a super high current and the wires catching fire. Okay, that's physically what's happening. So a circuit breaker is there to prevent a short circuit.
Does that mean the amount of electricity going back in the bulb is not zero? I mean, battery? It's not
Correct. That's exactly right, Brandon. So the charge carriers are leaving the battery with all this energy, but there's nowhere for it to go. If there's no bulb to take the energy, right, we said this bulb went out and now it's just connected, it would be like me taking a battery and just connecting a wire to it. I mean, we could do it actually, probably. You want to see it? Want to see if it'll burn maybe? It'll catch fire? Yeah. Oh, we should. Did you bring that up? You're the one that said it? There's also, I looked this up the other day. You could do it with pencil. You could take a pencil and use lead. Lead is graphite. It's metal, right? So you could actually draw a line with pencil, take each end of the battery, connect it, and eventually what will happen to the paper is the paper will catch fire. Because the lead will be carrying the current, but there's nothing to resist it. So all that energy would keep flowing through. It would be used by the battery, or it would be used by the bulb. So all that energy would keep going through the paper, and the paper would eventually catch fire. Let's see if we can do that. I don't want to take too much time to do it, but we can do it while we're waiting. Say again? We could try that, or we could also just use a wire. If someone has a gum wrap, we could try that too.
It's not the metal gum. And I do not bring gum to school.
How would you assume Darren has gum?
Exactly.
Anyone can use it, I don't have any today.
It's against the rules, Brandon.
I wonder if tinsel is magnetic also.
You must.
It's
What
in
if
the
tinsel?
tinky.
It did, right? So you think, well, no, but then that makes it a conductor problem. It needs to hold the charge.
Gum wrapper.
So, oh yeah, gum wrapper should be gum wrapper. Anyway, I want to get wires.
Oh,
Alright. Let's try it, see what happens. Maybe it doesn't work, maybe it does work. Try and burn some stuff. Alright. Let's see. Who likes to burn stuff? Raise your hand.
My hair.
Me too. I love burning. When I was a kid, my dad walked in my room one time. It's a true story. When I was a very young kid, my dad walked in the room, and I was sitting there, with a book of matches, my dad's deli, just burning paper. And I don't know why, but I love, and I still to this day, I like watching fire, you know, watching it burn. And he was like all like annoyed. He said, you know, you could burn down the house. What if we weren't home? What if something happened? So I learned better from that. But I still like to watch them burn. So by doing this, I'm not doing much because there's not much voltage going through here. But eventually, what happens is these wires will heat up. Anybody have that gum wrapper? Did you figure it out?
It's not the middle ones.
Anyone have another gum wrapper?
I don't know if it'll work. That has like foil around it.
Who waits to make these guys
You can try this one.
Well, it's 5 gallons of paper.
So I think we do have
Battery,
some.
water in that.
Water in that.
It's not gonna burn.
Aren't you supposed to wrap it around the battery?
It is so
Oh,
not
no.
gonna burn.
I watched it in Orange is the New Black.
Does anyone have an aluminum can and a chocolate bar?
Oh, yeah, it's like on my back.
Charge your phone and it'll be like rewired or something.
I guess that kind of.
No, I thought that shit like I just.
Oh, it's working. No, it's definitely working.
Oh, you're serious?
I can tell you it's working because the wire's getting really hot.
Um,
I don't want it to burn on the table. So I'm like looking around.
Smith and Wesson, like.
Wait, that's actually
I'm nervous that the wires
That's
get
crazy.
start to burn before the actual wrap.
yeah, because I don't think it's that kind of metal for the
Break
wrap.
that bad experiences with wires.
No, it's definitely going through the wire. I mean, feel the thing. You feel the wire.
Oh yeah.
Oh, it's definitely carrying.
Your phone.
So you support the show, so you support the, what's it called? The
Touch fire on
That's
that.
what it is, Smith and Wesson.
With the wires coming out for it. I mean, this is really hot right now. You squeeze it, you feel the heat coming off. Squeeze it. Don't hold it. Squeeze it.
Yeah.
Yeah, you're getting all over
I
it.
don't think you're
Feel the heat?
Oh, wait, yeah.
It's not like it's not like it's feels for sure.
Are we gonna put no stuff like omic and non-omic in the bra?
Omic and non-omic?
Yeah.
You should know the phrases for sure.
Steve comes in here just stencils and brings it over here. Just the fire.
Look at Winky Dink.
I mean, you touch it now it's like ridiculously hot. Touch the wire.
No, when it's connected to that.
Are you really a bagel?
Just trying to make fire. That's a good bagel.
Just notice the batteries.
It's overheating.
It's really hot.
Alright, Helen, you can beat that.
And the batteries are heating out too. I'm gonna stop because this is just I'm not wearing goggles, you're not wearing goggles. Alright, the idea though of a short circuit being that nothing is able to carry the energy from the battery, so it just keeps circulating through these wires over and over until the wires themselves just speed up so much.
No. I have like close wrap.
I'm just gonna toss it out. Unless you want to throw your number.
No, precious wrap.
I gotta look up a safe way to create a short circuit of fire. Maybe I'll do that for you guys next time.
Yeah, like that.
I might have been-
Just throw it in the microwave.
Oh, I go get that. Wiggle.
You know what's like you put like a bag, you put like a chip, like a bag, chip bag in a microwave, and like you run it, it like crumples up and foils and things.
Well, anything metal in the microwave is bad news bears.
Like a tiny version of it, it's so
Really?
Yeah, it's just like, if you would trace that, you can like flip it over a little bit, it'll be like this big.
Really?
Yeah.
And your microwave doesn't get ruined from that?
I mean, like, you know, it might, but it's not the important part.
Do it for the science. All right. Now, we went through the basics of circuits, right? And then we got into parallel and series circuits.
Yeah.
And we started talking about, like, hey, if they're in parallel, they have one law or one set of laws. In series, another set. So, yeah, let's take a look at what those are. So, in series, we remember that what's happening is this. The battery is connected only to one of the resistors. And then each resistor is connected to the next one in series, successively. So what we noticed for these problems was that the voltage supplied by the battery got split up to all of these guys. While the current from the battery is the same through all of these guys because it's not getting split up. That was the main rule that we looked at for series. But then for parallel, what we noticed was that each resistor was connected to the battery. Okay, each resistor is physically connected to the battery. So as a result, in this case, the battery is giving all of these the same voltage. But the current, because it's flowing through a pathway, and the pathway is branching off, the current splits up. So what do we know about these two rules? They're opposites, right? If you can't remember them, they're on your formula sheet, so you don't have to memorize them. But think about the logic behind it. Current is flow. If the flow doesn't branch off, the current doesn't branch off. Which is why in the first case, the current is the same for all resistors. But when the current does branch off, as we're seeing in this upper diagram up here, then it's the sum of all of those values. The sum of them.
You have to remember is one rule.
Yeah, if you remember one, you remember the rest. Exactly. But again, you don't have to remember any of them. They're on your formula sheet. Yeah, they're all on your formula sheet. And then resistors in series is a sum law. The resistance in series is a sum law, while the resistance in parallel, anybody remember what that's called?
Oh, R.
But what was it? It was not a sum law.
The reciprocal.
Reciprocal sum law. So it was not just RP equals, right? It was 1 over RP. So when I write this fraction, I want to recognize that my answer I get is not my answer. I need to use the inverse to get the answer. Okay? So the rules are very, very similar in nature, but they're very different, clearly, for series and parallel. Okay? I'm trying to think of what else I want to tack onto this for now.
What's IS on the formula sheet?
Series. So I use S and P on the formula sheet instead of B. Sorry, I use all these as P, P, P for these three, and S, S, S. S for series, P for parallel. See how there's 3 of each, right? Yeah. So today, I mean, this is really what we're looking at. This is our first one, the second one, and these are the ones we're looking at afterward. I'm going to get into these in a moment. Now, that's really the gist of it for circuits, but the key to remember is to do what for every circuit? When you're given a circuit with like 5 resistors, what's the first thing you have to do? Good. Find the total or equivalent resistance. If it's in series, Darren, then yeah, you're gonna. But if it's in, maybe it's like a makeup of series and parallel combination, you have to then look at that individually. So whatever's in series in that made-up circuit is the thing that you focus on first. So let's make up a circuit together real quick. Let's make one up. take a look at this circuit. I didn't give you the battery yet. Whatever, it doesn't matter what it is. Let's say it's 9-volt battery, but let's just say for now that's what we got. First, tell me in each area what's going on. So, in this first section, what kind of a setup are these two bulbs in? These two bulbs. What are they?
Series.
Why series?
Because they're in a line, parallel.
There's no junctions.
There's no junctions between them. From this bulb to this bulb, there's no branch occurring. So these must be in series. Yes? Second, these three are also in series. These two are in. So these are in parallel. These are in series, these are in series. But, look up. This branch with this branch with this branch is in parallel. So I've got parallel here, I can resolve into one. Series, I can resolve into one. Series, I can resolve into one. And then I'll have one resistor in each spot. And those three resistors that we get about are all in parallel with each other. So let's start by just summing these two together to get these, and then we'll do the reciprocal sum for these. So the first branch, what would the first branch have as an equivalent resistance? 5. And why do we know it's 5? Because it's just in series right now. What would the second branch have as an equivalent resistance? 9. Okay. 9 ohms. 3 plus 1 plus 5. So the first two resistors are very easy to get because they're in series. So anytime it's in series, do that first. Isn't that so easy, right? Now, what is the sum of 1 over 7 plus 1 over 4? That's the annoying part next, right? So if I want to calculate this last resistance, I have to do this. So I have to get the sum of 1/7 and 1/4 and then invert it.
0.4 approximately 0.4.
The answer comes out to be 0.4? Thank you. 1 over RP is 0.39 or RP is 0.39?
RP is 0.39. RP is 2.54.
Yes,
What do you get for RP?
2.545.
So take a look at what we're doing. If you don't make sense of this, please ask. We've got two resistors in parallel. There are 7 and 4 ohms. From our notes in class, we know that the result has to be less in resistance. How do we get rid of this 0.39 and get to this answer here?
It's reciprocal. Or the log.
Yeah, we flip this side, right? We have to reverse this side to get RP by itself. So we also need to reverse this guy. What is this currently over, though? So let's do 1 divided by this number instead.
Multiplication.
And we should get around 2.54. Now, there's a key on your calculator that says x to the negative 1. That does 1 over for you. It just does it for you. So when you get 0.39 as your answer, you can then just press x to the negative 1, and you'll get the reciprocal. So if you do the 0.39, so do 0.39, x to the negative 1, hit enter. You get the same value. Okay? So again, it's important to note how to get it. Now, are we done? No. Because now we've got 3 resistors left over. And what are these 3 resistors in?
Parallel.
Which one?
That's 3.
Which you gave it your answer?
Parallel.
Parallel. Why are they in parallel? Take a look. Junction before this happens. Junction before this happens. So these 3 bulbs are now in parallel. So what I'm going to have to do is do another reciprocal sum. I'm going to use blue. I've got to do another reciprocal sum. 1 over RP equals 1 over 5 plus 1 over 9 plus 1 over 2.54. What do I get when I add those 3 fractions together before inverting? 1/5 plus 1/9 plus 1 2.54.
0.704.
I just want verification that we all got it, right? Invert that?
1.41.
So again, let's look at the answer and make sense of it. I had 3 resistors in series in parallel right here. 5, 9, and 2.54. And we keep saying this over and over again. When something is in parallel, the overall resistance will go down. It's always going to be less than any of these 3 or the lowest of these 3 resistors. So whenever you have a parallel setup, the answer you get when you resolve parallel resistors should go down. Again, 2.54 was the smallest. Our answer is less than 2.54. It's not a coincidence. It has to happen every time. In series, because you're adding the numbers together, the overall resistance goes up. So if overall resistance goes up in series, the overall current goes down in series. Again, think about that for a second. If the overall resistance goes up, it means the overall current goes down in series. But then in parallel, we're seeing that the resistance goes down, right? The resistance lowered from 5, 9, 2.54 to this number. So for the resistance to go down, the current has to go up. The current has to go up.
So what type of question would this be?
Oh yeah.
Like, no, this one.
This kind of question?
I
I would probably ask you to resolve the circuit into its equivalent resistance. So at this point, once you've done that, once you've done this, you would then just redraw the circuit with only one resistor of 1.41 ohms. So you would start with the first setup, the second setup, and then the third setup.
You have to do math first before you get there.
You would have to do the math that we did with the resistors, But then once we get to this point, all I would ask you would be to find the current. And to find the current in the circuit, very good. And then do the voltage, which is 9 volts, divided by the resistance of 1.41 ohms. And you would get the current there. Now, this is a more complex arrangement because I have series and parallel together. So you could definitely expect one of these where all you're doing is getting the current at the end. But then if you go back into your notes, you'll see that I also had you guys figure other stuff out. I have all series, like this, right? 3 in series, like that. Then in that circumstance, it's a quick answer. Like say this is 2, 3, and 5. Well, the sum of 2, 3, and 5 is just going to give me 10. So that's not all I'm going to ask you to do for this problem. So for a problem like this, you're going to find the current, sure. The current from the source is going to be the voltage divided by the resistance. So you can find the current, but then I might ask you to do stuff like find the voltage dissipated by each bulb. So if I want voltage, I take current times resistance. The current through each bulb is 1.8, and the first one has a resistor of 2. And then I would do the same thing for the second bulb, and the same thing for the third bulb. Hey, the last thing we didn't get a chance to talk about real quick was power. Power, you got to know that you got 3 formulas, depending upon the scenario. Formula 1, Formula 2, Formula 3. You could use either of those 3 formulas to get power. Okay, I would recommend looking at that and then looking at the idea of cost. Remember, cost is the amount of energy times the energy rate. Okay, that was at the very end of the notes that day, and I recall you did these notes with Steve. Am I correct? Okay, so what I would recommend is that you guys have 2 days. I don't see you tomorrow. Tonight, go back and practice more, but specifically watch the video on power to reiterate that because I was not here for power. So I want you to make sure you hear everything that I wanted to say that day. You can come see me if you need help tomorrow or Wednesday morning at the latest. Okay? Don't worry about the labs right now. Do not worry about the labs at all right now. Okay? We'll talk about those more. Have a good day, guys.